Hello, Matthews, Gatos here. We're going to do Chapter 2, Lesson 6, which is Part 2 of Combinations. So let's just jump into an example here. Let's say we have a student council and they want to form a subcommittee with 5 members. There's a total of 11 student council members. 5 of them are males, 6 of them are females. So we want to know how many different 5-member subcommittees can be chosen. Now I could end the question there. They added on if there are no restrictions on the number of males or females, but I could just say how many different ways can this 5-member committee be chosen. So first of all, we have to decide, is this a perm or is it a com? So it is a combination, and the reason is there's no assignable roles, tasks, or positions, okay? So that's what makes it a combination. So I just want to look at, in general, how many ways can I do this? So there are 11 members, and I am going to select them 5 at a time. So this is just an 11C5 question, which I can put into my calculator, as I did here, and you can see that the answer is 462 different 5-person committees. So let's add some restrictions to this committee choice. So let's look at how many ways we can have a 5-member committee with exactly 3 females. Now, exactly 3 females means I can't have 1, 2, 0, 5, 4. It has to be only 3. Now, the big hint here is that it has to add up to 5 members. That's really key. We need 5 members on our committee. So if I have 3 females, I have to have 2 males. So let's look at the females. There are 6 of them, and I want to select 3. And then looking at the males, there are 5 of them, and I want to select 2. The reason I'm multiplying those together is because it is an AND question. So 6C3 times 5C2. And again, I can put that into my calculator just like that, and you can see I get an answer of 200. So there are 200 committees with exactly 3 females. Now let's change that from exactly 3 females to at least 3 females. So at least means minimum. So when I say at least 3, it means a minimum of 3 females. So I can have up to 5 members. So you can see I've done 3 females, 4 females, 5 females. But I have to remember it always adds up to 5 people. So with those females go the males. So let's fill in the females first. I have 6 females, and in this case I want 3. 6 females, I want 4. 6 females, I want 5. Now, with those have to go the males because I have to add up to 5 members. So for the boys, I have 5, 5, and 5. So I'm going to do 5C2, 5C1, 5C0. So again, we're multiplying these together because those are the ANDs. 3 females and 2 males. So we have to decide what we're going to do with the cases, and the cases are connected together with OR. And hopefully you guys remember that OR in math means add. So we need to add the cases together. So we can put that all together in our calculator in one keystroke, just like that. And I can see that there are 281 5-person committees with at least 3 females. Okay, let's move to a card question. So card question, and I have a visual there to help us with it. There's 52 cards in the deck. We want to know how many 5-card hands can be formed, and it says with no conditions. But again, I would just say how many different 5-card hands can be formed. So card questions are combination questions because when I get my cards in my hand, I can shuffle them around and it's still the same hand. So the order that I have the cards in my hand does not matter. So because there are no restrictions, I'm just looking at 52 cards and I need 5 of them. So 52C5 is what I'll put into my calculator, and you can see I get this big number here. It's 2,598,960. So let's start to put some conditions on these questions. So let's look at how many 5-card hands can be formed with at least 4 red. So you can see I've color coordinated it there with 26, half the deck is red, and 26, half the deck not red or black. So at least again means a minimum. So let's start with the red cards. If I want at least 4 red and I have 5 cards in my hand, I have either 4 red or 5 red. So looking at the red, there's 26 cards and I want 4 of them, 26 red cards and I want 5 of them. Okay, now let's add on the next layer of this question, which is the black cards that go with it. So I have 26 black cards and I want 1, and 26 black cards and I don't want any. So we're multiplying together again because that is and. So I want 4 red cards and 1 black. And then I have cases, which is or, and or in math means add. So putting that together in my calculator, you can see that I have 454,480 5-card hands with at least 3 red. Okay, in this next question, we're seeing a new word here, which is at most. So at least means a minimum. At most means a maximum. So I'm looking for how many 5-card hands have at most 2 kings. So you can see I've color coordinated it there. So you can see that there are 4 kings in the purple, and there are 48 cards that are not kings. So at most, again, is a maximum. So we're going to have cases again. So at most, no more than. So I could have 0 kings, 1 king, or 2 kings. So let's fill those in. We'll focus on the kings first. So I have 4 kings, and in the first case, I don't want any. 4 kings, and then I want 1, 4 kings, and then I want 2. So now let's focus on the not kings, because I have to add to 5 cards in my hand. So if I have 0 kings, that means I have 5 cards that are not kings. So there are 48 not kings, and I want 5 of them. And then to go with the 1, I need 4 not kings. So 48, and I want 4. To go with the 2 kings, I want 3. So 48 not kings, and then 3. So again, multiplying because that means and, 0 kings and 5 not kings. They're individual cases, so I'm adding them together. So I can put all of this into my calculator, and it would look like that. Okay, so all together, I can see that I have 2,594,400 5-card hands that have at most 2 kings. Okay, I want to look at this idea of at least and at most in a little bit more detail here. Okay, so remember where we had 462 ways where we could have a 5-member committee with 5 males, 6 females, and we wanted how many have at least 1 female. So the way that we solved that, or we can solve that in class example number 1, to have at least 1 female would mean that I would have 1 female, 2 females, 3 females, 4 females, or 5 females. Okay, now because it has to be a 5-member committee, I have to add 1 female with 4 males, 2 females with 3 males, and so on. And you can see I've done all of my different combinations there, and I can plug all of that into my calculator. Okay, so there it is all together, and I can see that I do in fact get 461. So 461 5-person committees with at least 1 female. Now that way of doing it is totally fine, but I want to show you another way that we could look at this question. Okay, so Alicia realized there's a quicker way to solve this question. So instead of doing all of the cases like we did before, the only case that we're missing is 0 females. So if I go back here, look what we had. We had 1 female, 2 females, 3 females, 4 females, 5 females. It's only 5 people on a committee, so the only thing we're missing is the 0 females. So remember when we did questions like this where it was all minus can equals can't? It's the same idea. So the total number of committees with no restrictions are either going to have 0 females or at least 1 female. Those are the only possibilities. So what I can do is say, okay, the total is 0 females plus at least 1 female. So the total minus no females would be my at least 1 female. So instead of doing all of this work here, I can just do this quite simply. Okay, so the total number of committees with no restrictions we already know is 462. That's what we did in the very first question class, example 1. And then I can just take away the committees that have no females. So 0 females and basically all males. And plug that into my calculator. And I just get this. Okay, same answer as before. So with these questions, if you feel comfortable listing out all of the cases and doing it, that is totally fine. This is just another option that you can go with. So let's look at, in general, anytime I have something like that, I can always do the total minus the smaller case gives me the bigger case. So what we did with Alicia's work, we can omit the first 3 steps in her solution and just say all minus none equals at least 1. Just simply like that. So sometimes there will be easier ways of doing it, and I just want you to be on the lookout for those. So let's give that shortcut method a try. So we'll do it both ways, but I want to show you the shortcut method here. So we have 52 cards in the deck. We want a 5-card hand with at least 1 club. Okay, so at least 1 club means a minimum. So I can have 1 club, 2 clubs, 3 clubs, 4 clubs, or all 5 clubs. Now with all of those clubs, because I have to add up to 5 cards in my hand, go the not clubs. So 1 club and 4 not clubs, 2 clubs, 3 not clubs, and so on and so on. So I can put all of that into my calculator. It was such a long thing for me to copy. I had to do a split screen to get all of it. That is a lot of work. Now, if you want to do that, that makes you feel more comfortable, that is totally fine. But I just want to show you how we could apply the shortcut that we just did here. So the only case that's missing is 0 clubs. So at least 1 club would be all of the cards with no restriction minus all of the ones that have no clubs. So all the cards no restrictions would be 52C5. And then I'm going to take out all the hands that don't have any clubs. So they're all going to be not clubs. So there's 39 not clubs, and I want 5 of them. So if this method works, we're going to get the same answer as we did right here. So plugging that into my calculator is so much easier in my opinion, and you see that you can have a match. Okay? So either way that you want to do it is totally fine. It just comes down to preference. Okay. So the last little thing I want to talk to you about is combinations which are equivalent. Okay? So Fran and Bernie have identical collections of vintage toy vehicles. They all have 10, and you can see they're the same. So Fran selects 2 toys from the 10 to show on display. So she has 10 toys and she selects 2 of them. Now it doesn't matter the order that you select the cars because they're all going to be displayed. So she plugs that into her calculator and sees that 10C2 is 45 ways that she can do that. Now Bernie, however, he wants 8 cars. So he's going to select 8 cars from his selection. So he has 10 cars. He wants to select 8 of them. So he plugs into his calculator 10C8 and he gets 45. So those are equivalent combinations. Now the reason that they're equivalent is because Fran picking 2, Bernie picking 8, those 2 add up to 10 altogether. So a simpler way of saying this is you could say that Bernie had 8 cars that he selected, which is the same as Fran selecting 2. So if you have 10 cars and you select 2 cars to be on display, that is the exact same thing as not selecting 8 because 2 and 8 add to 10. So those are equivalent. Let's look at that in a little bit more detail. So the reason that 10C2 is the same as 10C8 is that taking 2 is the same as not taking 8. So for example, Bernie taking 2 was the same as Bernie not taking, Bernie took 8. Bernie taking 8 is the same as him not taking 2. And Fran taking 2 is the same as her not taking 8. That's why they were equivalent. So let's look at that using the formula, just to see the formula, so you can see a mathematical way why it's the same. So using my formula NCR, I put the n factorial on the top, I subtract n minus r factorial here, and then I take my r factorial there because the order doesn't matter, so I divide by that. So let's plug that in using 10C2. So 10C2, the 10 factorial goes on top, and then the 10 minus 2, which is 8, goes on bottom, and then the 2 also goes on bottom. So I want to see if that's the same as 10C8. So I want to know, is this the same as 10C8? So let me do that in a different color. Okay, so I do 10 factorial on top, and then I do 10 minus 8, which is 2 factorial, and then just the 8 factorial. And you guys can see, because multiplication is commutative on the bottom, 8 factorial times 2 is the same as 2 factorial times 8. So you can see mathematically that those are the same. So if I wanted to give two other examples of equivalent combinations, so let me write this one down, 5C3, and then you can just pause the recording, write down an equivalent combination to that, and come back and see if you got it right. So what would be equivalent to that is 5C2. And again, that's because 3 plus 2 is 5. So let's try another one. If I gave you 7C4, so again, pause the recording, write down an equivalent combination to that, and then come back and see if you're right. So what would be equivalent is 7C3, because 4 plus 3 add up to the total of 7. Okay, so those examples illustrate this rule here, that having n objects and taking r is the same as having n objects and not taking n minus r. Or again, remember that alternate form of combination notation. This is NCR and this is NCn minus r. So those are a rule that can come up from time to time. So we're going to omit all of that. That's a challenge question, not part of the curriculum. And we'll go to our summary. So in our summary, at least means minimum, at most means maximum. So watch for cases and add the cases together. Okay, remember that if you have many possibilities, you can use that little shortcut, which was all minus this big case equals to the case that you're looking for. So look for complementary events. And then NCR is the same as NCn minus R. So lots of formulas for you guys to look at in this section. And in the Math Art Museum, we have these types of formulas on display because they're very good, and I do appreciate them. So that's the end of our lesson. You guys can do your practice questions, and then when you're done, you can look at lesson number 7.